Okay, this is part 2 of our introduction video concerning surfaces of revolution and how to find their volume. In the last video, we derived a formula, a volume integral, if you will, that was applicable when we formed a solid three-dimensional figure by taking a curve and we rotated that curve around the x-axis. Now we want to consider what kind of a volume integral would we have if we took a curve and we rotated it instead about the y-axis. So here we have our diagram. This is the curve, and we imagine taking this curve and rotating it all about the y-axis to generate this solid two-dimensional figure. And we want to know, how can we find the volume of that figure? So we proceed much as we did in the last video. We consider our curve here, and this curve is being rotated about the y-axis. And here we're considering a very thin strip, a thin volume strip, if you will. Imagine we have this thin strip here, and this is being rotated about the y-axis to give us a thin strip of volume. And we're calling that thin strip of volume delta V. And we want to know, if we don't know exactly what that volume element is for that strip of volume delta V, can we get an approximation to it? And that takes us over here to this diagram. Here we have the curve. We're going from y equals 0 up to y equals b. And here then is the basis of our volume strip. We will go over to here, only now we're going to make a rectangle. And the height of this rectangle is at a distance x from the origin. Now notice that when we're making our rectangle, we're clipping off part of the element here that comprises this volume element delta V. So we have to keep that in mind, that what we're doing is only going to be an approximation to delta V. And with this rectangle then, we rotate it about the y-axis, and that would form then a flat, solid, circular disk. The radius of that flat, solid, circular disk would be delta x, and the thickness of it is, the radius of the flat, solid, circular disk is x. Its thickness is delta y. We try to sketch it out here like this. This would be our flat, solid, circular disk. Its radius is x, and its thickness is delta y. And what would be the volume of it? It would be the area of this circular face multiplied by its thickness, delta y. And the area of that circular face, of course, is pi r squared, only the radius in this case is x. So the volume of our flat, solid, circular disk is pi x squared times delta y. And this volume here for our flat, solid, circular disk, that's an approximation to this strip of volume that we created over here, delta V. So we can say that delta V approximately, that's approximately equal to pi x squared times delta y. Now here in this diagram, we only made one rectangle, but imagine starting down here at y equals 0, and we could draw a whole series of rectangles all the way on up until we reached y equals b. And for each of those rectangles that we made, we can rotate them about the y-axis to form a flat, solid, circular disk. Each one, of course, has a certain volume associated with it. And as we keep doing that, we keep adding up the volume all these circular disks that we make, that would be an approximation to the volume of our solid figure up here. So we can say that the total volume V, that's approximately equal to the sum of all these circular disks that we have, adding them all up, starting at y equals 0 and going on up to y equals b. Now imagine, as we're going through this process, that we can make delta y smaller and smaller. As we're doing that, then, we're clipping off less and less of this element over here. So, as we continue refining our process, the volume becomes a closer and closer approximation to our stripper volume, delta V. And imagine then that delta Y is approaching 0, so now we have differential Y. So imagine here we have infinitesimally small dy's here as a basis of our circular disks. Now we want to add up the volume of all of these circular disks that have a thickness of dy. Then as we do that, that will give us the exact volume of our figure. So we would say then that the volume, that will equal the integral of pi x squared dy. And we start adding. We don't necessarily have to start at y equals 0. We can say in general, beginning at y equal a, and continuing up to y equals b. So this then would be our volume integral, and we form the solid figure by rotating about the y-axis. Now, in the last video, we derived the volume integral when we formed our solid figure by rotating about the x-axis. And we can generalize it. What we can say is that if you form a solid three-dimensional object by taking some line or some curve and rotating it about any horizontal line, then in that case the volume, that's equal to pi times the integral of y squared dx, starting at x equal a to x equal b. Now this is when we form the volume element. We don't just have to rotate about the y-axis, we can rotate about any horizontal axis. Only in this case, we have to be on the lookout. Y has to be expressed as a function of x in order to perform our integration. Now if we form our solid two-dimensional object by rotating about a vertical line, then the volume of it becomes this. And now we start at y equal a to y equal b. And in this instance, x has to be expressed in terms of the variable y so we can perform our integration. So anyway, that's the conclusion of our introductory videos. Hopefully they're worthwhile. We tried to take some time and just kind of use a basic common sense approach to show how these two different volume integrals are obtained depending upon whether we're rotating about a horizontal line or a vertical line. And come back, join us now for some more videos, and we'll use these volume integrals here, and we'll start solving some specific problems with them.